Hello, I'm Dr. John Kruse, and today I'm going to be talking about the prefrontal cortex and ADHD. What's the connection? So as usual, I'll start with the take-home message, and after about 2 or so minutes, I'll jump into the main body of the talk. So the take-home message is that the prefrontal cortex is the location, the body, embodiment, or where the executive functions of the brain occur. Those are central to problems connected with ADHD. So executive functions are things like working memory, prioritization, selective attention, how our brain works to create goal-directed projects and accomplish things. And although neuroscientific, neuropsychological testing can tease out and find ways to test and verify and research separate executive functions, one of the things that's important regarding the prefrontal cortex is that there's a great deal of interconnectivity between these different functions, and there's also what I would call recruitment. So if one system is being taxed, it engages more of the whole prefrontal cortex in general, and that's substantially different from much of the other brain regions, which are narrowly focused on their task and don't recruit others. So if you're looking at lots of different things, your visual cortex doesn't start recruiting other sensory areas because it just can't process so much visual information. But again, in the prefrontal cortex, there is recruitment, there is slop or interconnectivity, and there's also fatigability. So we often use the metaphor of muscles when we're talking about the brain, and so it's not surprising to us that parts of the brain, if you use it too much, can strengthen over time like a muscle, that it might get tired or wear out, but most of the rest of the brain isn't fatigable in that way. So again, looking at the visual cortex, if you're looking at something, really, really intently, your eye strain may happen, but your brain doesn't get tired. Your brain doesn't have trouble processing looking at one marble versus looking at 1,000 marbles on a floor, even though the task is 1,000 times different in some ways. Or you can look for 1 minute, you can look for 50 minutes at your marbles on the floor. Your visual cortex is not fatiguing and unable to process that visual information, whereas with many of the prefrontal cortex executive function, there is fatigability. If you put too much burden on it, it just can't accomplish that task or does it much more poorly. And tied in with this is that the prefrontal cortex is stress dependent. So how it functions has to do with the overall state of the brain or the overall state of arousal of the brain. And this is part of why stressed out brains, too anxious, too depressed, too PTSD, too traumatized, the deterioration in executive functions from those conditions isn't just resembling what's going on in ADHD. I would say it is creating the exact same underlying difficulties in executive functions that we see in ADHD. So jumping into the main talk. So the prefrontal cortex, and sort of the question is, what's it in front of? It's in front of the motor cortex, which is a strip of the brain sort of about here, down in, which controls movement of the body. This is the area in front of that, so prefrontal. It's the newest part of the brain evolutionarily. So in the time that our brains evolved from our early primate ancestors and approximately tripled, our cortex tripled in volume or size, the prefrontal cortex actually sextupled. So not only did our whole brain grow bigger, but preferentially this part of our brain grew much bigger. And one other special thing about this brain at a sort of neurochemical area, glutamate is our most common neurotransmitter in the brain. It is an excitatory neurotransmitter. but there's a particular dependence on a subset of glutamate receptors called the NMDA receptors in the frontal cortex rather than the other types of glutamate receptors found out the rest of the brain. So not just with ADHD, but with almost all of our mental health conditions, schizophrenia, depression, anxiety, PTSD, there are certainly other parts of the brain that are involved. ADHD, the cerebellum's involved, the thalamus is involved. But most of the research, most of the interest, most of the findings have evolved. The executive functions which are housed in this area are so critical, important to all of these mental health conditions that that's where most of the activity, most of the interest has been happening. So again, what are executive functions? Are things like working memory, top-down attention, emotional regulation, organization and planning, sort of how your brain works to accomplish tasks. And what I'm going to be saying next is there's a lot of it's involving oversimplification. So dividing the prefrontal cortex into two sort of main categories. So there's a dorsolateral and prefrontal cortex, and there's ventralmedial. So dorsum, like a dorsal fin on a shark, if there's dorsal, it's the back. Anatomically, humans are sort of weird in terms of their posture, but dorsum is going to be the top surface, lateral is sides, ventral, where your vent is to let waste products leave your body, is your bottom, your underside. So it's the underside of your brain. So ventralmedial is sort of down and under. Anyway, the dorsolateral prefrontal cortex is especially connected with brain regions involving what are called cool or cold reasoning aspects of executive functioning, like self-regulation, working memory, planning. So it includes cognitive control, which how do you make decisions? How do you decide what working memory? And working memory, again, is the information you need to keep in hand for a few seconds at a time to complete a task. So it's remembering, I've picked up my keys, but I'm in the way to get at my wallet. You're not dropping off one. You're keeping track of one without maintaining it in your eye contact or others, so you can get a task completed. Top-down directed attention. So top-down directed attention is what you decide you want to be focusing on. So some call it selective attention versus bottom-up attention is what in the environment's popping out as important or salient pay attention to. So dorsolateral prefrontal cortex, involved in top-down attention, cognitive control, things like decision-making, working memory, goal-directed behavior, identifying goals, understanding the future consequences of your behavior, countering emotional biases. So it's overriding emotional biases and deciding what's rational or socially appropriate, even though you might feel like doing something otherwise. Dorsolateral prefrontal cortex is also involved in deciding which rule to follow when there's two conflicting rules or decisions. So it's also involved in flexibility in decision-making and prioritization. And it's also involved in the cognitive regulation and control of fear. So in contrast, the ventral prefrontal cortex is often considered the hot region, and hot means more emotional, more hot-blooded. So it's involved in emotion, reward, and value decisions. So emotional there's lots of connections between the limbic system, the amygdala, hippocampus, fornix, other areas involved in emotion. So the ventral prefrontal cortex is involved in helping generate, regulate emotions and controlling emotional reactions. It's also involved in memory representation and that's sort of integrating emotional aspects and sensory aspects of a memory together. And creating representations in the brain as well as concepts of the self within the brain. This is also the ventral prefrontal cortex is involved in social cognition, such as facial recognition of emotions, the theory of mind, processing self-relevant information. It also has a role in controlling actions or physical behaviors. So we often describe these as very separate modules and tasks. And again, with intricate neuropsychological testing in a laboratory situation, we can tease out these executive functions as separate, discrete, identifiable tasks, although many real-world tasks combine multiple executive functions at the same time. And in the real world, in the operating brain, it looks like, compared again to many other brain regions, one, there's much more interconnectivity and cross-wiring, but also more recruitment of other areas. If your working memory is too tired or exhausted, then that's having an impact on other executive functions directly and immediately. So this gets to part of why the prefrontal cortex is more vulnerable. So there's a couple different levels of vulnerability I'll talk to. One is just genetic vulnerability. So we know a lot of the propensity for ADHD, for depression, for schizophrenia are genetic factors. So clearly, how someone winds up being wired, their biological predisposition does affect how well the prefrontal cortex and executive functions may be working. But there's also inherent vulnerability due to the anatomy. I mean, this is a big area of your brain. Therefore, you're facing trauma, and it's not just a big area, it's a forward-leading. We generally move forward in life, it increases the likelihood of damage to the front of the brain. It also involves longer projections in average than in much of the brain because they're coming from deep brain stem and thalamic and other internal structures. It's a longer distance. We know lots of the damage from trauma isn't just direct concussive force, but shearing, physical forces being shaken and twisted and shearing within it. So that makes it more vulnerable. And again, there's a greater degree of sort of interconnectivity, lots of dense connections. So damage to one area may well have impact beyond that narrow, discrete area. Another area of vulnerability is the neurochemical one. So again, glutamate receptors in much of the brain are AMPA receptors. Those are quick responses. So like in the visual cortex, glutamate's released. It has a quick response generally on the AMPA receptors. The NMDA glutamate receptors work a little more slowly, and that may be part of tied to the next connection, which is fatigue. So again, we make analogies all the time to the brain being like a muscle, but most of the brain does not fatigue. So muscles do fatigue. So yes, muscles wear out at different, a bicep doing curls wears out more quickly than some of our postural muscles that are important for our standing up or sitting down or maintaining posture. But all of our muscles, with enough time, with enough effort, get tired and fatigued. Most parts of our brain keep functioning as well as we're alert and aroused, or not even, whereas again, the frontal cortex gets tired. It has finite reserves. And some of the executive functions controlled within the prefrontal cortex do compete with each other. So if there's too much demand placed on working memory, if you're asking someone to keep track of 5 different numbers and then you give them a task where they have to switch between different strategies, there is competition, there is fatigue, there is the whole system collapses because there are too much of a demand on the system. So again, this is unlike other areas of the brain. This is unlike this is more like muscles in some ways. So the other aspect of why this prefrontal cortex is more vulnerable is that it is, again, arousal dependent or stress dependent. And I'll get into this in a little more detail. So much of this is based on decades of work by Amy Arnsten and her colleagues at Yale and outside of Yale. Particularly, she's looking at cortical layer 3 in the dorsolateral prefrontal cortex and looking at working memory models and looking at the NMDA glutamate receptor system. So under low stress, sort of normal operating conditions, the NMDA glutamate receptor is an ion channel receptor, so it regulates the flow of calcium, that activates cyclic AMP and protein kinases, which then go affecting potassium flows in and out of the brain. That NMDA receptor, glutamate receptor, also requires actually some acetylcholine binding on that cell that has received the glutamate. So the acetylcholine binds to a nicotine alpha 7 receptor, which allows things to happen. There's other neurotransmitter receptors on those glutamate receiving cells. So the norepinephrine receptors, so the alpha 2A receptors, under normal amounts of norepinephrine, so someone's not stressed out, just a low baseline level, those binding to the alpha 2A receptors actually inhibits the formation of cyclic AMP and protein kinases, changes the amount of calcium flow and eventually potassium flow. And this actually, within the prefrontal cortex, strengthens synaptic connectivity. So under low stress conditions, normal amounts of norepinephrine and dopamine being present, the prefrontal cortex connections, the synaptic spines are built up. There's strengthening connections. But under situations where dopamine or norepinephrine are at excessive levels, high levels, then rather than binding as much to the alpha 2A receptors, the norepinephrine binds to alpha 1A receptors, the dopamine binds to dopamine 1 receptors that are, again, also on these cells with the glutamate NMDA receptor. This increases calcium flow, it increases protein kinases and cyclic AMP signaling, and this rapidly opens potassium channels, changes which nerves are going to fire. And that effect is actually to weaken the interconnectivity, to decline synaptic connectivity within the prefrontal cortex. And that functionally weakens working memory. It weakens other executive functions. So under high stress conditions, you're causing a deterioration in executive functions. In contrast, the effects on the amygdala, it's our basic emotional bottom-up, emotional part of our brain processing system, stress actually strengthens the synaptic connections with the amygdala. And not only are these acute changes, we can see chronic changes with stress. So with long-term stress, there is further deterioration or weakening of synaptic connections in the prefrontal cortex. There is deterioration of many of the executive functions, whereas there is stronger consolidation of amygdala functioning, so you are more driven by emotional impulses and less able to sort of top-down regulate or control them. And this is why conditions like anxiety and PTSD mimic ADHD. So they are causing a deterioration or a disconnection or a weakening of some of the prefrontal cortical circuitry and executive functions within the brain. So it's not just like anxiety sort of looks like ADHD, I would say at a brain functional level, it seems to be mimicking, it seems to be creating those same conditions in certain parts of the prefrontal cortex. So another Yale professor, Mark Rego, psychiatrist, more clinical work, has written a book called Frontal Fatigue, where he argues that much of our stressors in modern life, so there's an increase in complexity, not just with technology, but that's a big driving force, but even our urban environments, other aspects. We're dealing with more complexity. We're dealing with much more abstraction rather than hands-on, real, physical seeing. If I do A with my hand, that results in this in the world. Most of our calculations, most of our work, most of our how we're dealing with things, particularly with the computer, is an abstraction. We're also needing to reformat, rechange. It's not just updates in the operating systems, but things in life are changing much more quickly than they did for thousands of generations of people. Our environment's changing more quickly, and we have more decision-making required of us. So all of those stressors of modern day life are wearing down these prefrontal cortex. They're causing a situation of higher stress, higher norepinephrine dopamine present, which is decreasing synaptic connectivity within the prefrontal cortex and contributing to that. Again, this is a part of the brain that's susceptible to fatigue. So one of the thoughts, directions my questions go into this is, one is clearly our current psychiatric labels are not, some argue they're meaningless, some say they're not the best way to really separate out different conditions and what may be going on. Some argue about whether there are conditions or not. Clearly there are social factors. The National Institutes of Mental Health for more than a decade now has been trying to get and encouraging and has successfully gotten people to research more on what are called research domain criteria. So that's rather than looking at diagnostic conditions, but encouraging researchers to examine functional processes and look at them on a continuum between normal and abnormal and try to make connections and correlations between brain processes that are going on and how that's manifesting in terms of thoughts, behavior, feelings in the real world. And again, it eventually it's already sort of undermining our concept of what is something like ADHD. Yes, we define it as a set of symptoms, but maybe it would be more helpful to define it as disturbance of or aberrant patterns in executive functions connected with prefrontal cortex disruptions. And if we do things that way, then we may not be saying, oh, you have trouble concentrating because of your anxiety. If that trouble concentrating is happening at the same neurologic level as trouble concentrating from ADHD, maybe it's better just to call it trouble concentrating rather than to attribute it to either. And it underlies almost every condition in our DSM-5 psychiatric diagnosis, after it lists symptoms, after it lists other criteria for the condition, puts in not due to another condition. So our whole system is based on rule-outs, and yet what we're ruling out is other conditions whose ultimate origins, etiologies, we don't know either, which doesn't make a lot of sense. When someone breaks a leg, they've broken a leg, and we treat it as a broken leg. Now, it might be due to partly because they had osteoporosis, weakening of the bone. It might be just a traumatic injury. They were involved in a car crash. It might be that factors related to benzodiazepine use or hydrocephalus made their balance less stable and more prone to a fall. So there could be lots of different origins and pathways and contributors to it. But we don't rule out, we don't say, oh, well, you have osteoporosis. That's why you broke your leg. We're not going to treat you for a broken leg. So we often pretend that other fields of medicine don't primarily focus on symptomatology. They often do, and they need to do, and they don't rule out things just because other conditions are contributing to them. So that's where I will end my talk about prefrontal cortex. Again, it's central to ADHD, and unlike other brain areas, its fatigability, its leading across different functions when one function is stressed out or overwhelmed, is an important part of the consideration of what's going on in ADHD. So stay healthy, stay happy. Thanks for listening. And I'll have questions and answers on this in a few days. Feel free to write down questions or comments.